Let us look at a practical situation where one needs to assess how natural frequency of a turbine blade varies across the spools of a gas turbine engine. Spools meaning mechanically independent systems which rotate at different speeds. The assessment involves the idealization of the geometry, operating conditions. In each spool, the compressor stage is driven by a turbine stage, meaning in high pressure spool, the high pressure turbine is connected to a high pressure compressor such that the work produced by the turbine is fully consumed by the compressor stage. Since lot of work can be extracted from one stage of turbine owing to a favorable pressure gradient, that is dou P by dou X is less than 0, meaning the pressure is dropping continuously, it can drive many stages of compressor. This is because the compressor has an adverse pressure gradient, that is dou P by dou X is greater than 0, meaning the pressure is increasing continuously and only a small amount of work can be absorbed in each stage of compressor. The temperature across the HP compressor for a typical civil gas turbine engine is as high as 600 degrees centigrade and goes higher than 1100 degrees centigrade in the HP turbine stage. As the temperatures are significantly high, they soften the material, bringing down the Young's modulus significantly. The variation of Young's modulus with temperature for Inconel is as tabulated. We can observe that for a temperature of 649 degrees centigrade, the reduction in Young's modulus is almost 20%. Which in turn reduces the natural frequency by 10.5%. We know that natural frequency is proportional to root of Young's modulus, and therefore the natural frequency due to high temperature is proportional to root of 0.8 E, owing to a 20% reduction. Therefore, the reduction in natural frequency can be computed as F1 minus F2, that is, change in natural frequency to the original natural frequency F1, which in turn is given by 1 minus root 0.8, which is equal to 10.5% reduction in natural frequency. Now, let's evaluate how the natural frequency of a turbine blade varies across the three spools of a typical gas turbine engine. It can be observed that across the spools, the temperature decreases, but the blade length increases. If we assume the blades to be cantilevered beams, then we have three counteracting effects. The temperature brings down the Young's modulus and hence the natural frequency. The natural frequency decreases with increase in length as it is inversely proportional to the root of cube of the length. As we move across the spools, the RPM decreases. However, the blade length and blade mass both increases. The increase in centrifugal loading brings about the stress stiffening, meaning increasing the flexural natural frequency of the blade. Therefore, it is clear that the natural frequency decreases with temperature and length. However, the flexural natural frequency is increased by increase in centrifugal loading. In summary, we have the following.